Let us see about three-phase half-control rectifier or semi-converter. First, we will see the difference between a fully controlled rectifier and a half-control rectifier. This fully controlled rectifier we have seen in the last video. So, it consists of 6 thyristors, and a half control rectifier, as the name implies, it consists of thyristors as well as diodes. So 3 thyristors and 3 diodes will be there in half control rectifier. So this rectifier is also called semi-converter. It means that you cannot control fully, whereas you can have a limited control over the output voltage. So it is called a semi-converter or half control converter. So what are the basic differences between fully controlled rectifier and half control rectifier is that here regeneration of power is possible. That is, power can flow from AC side to DC, or it can also flow from DC to AC. So voltage can be positive or negative. That is, the average voltage can go positive or negative. Here you have 6 thyristor. So the cost of the thyristor is high, and whenever you have thyristor you will get associated gate circuit. So you need gate circuit for each and every device. In half control rectifier, regeneration of power is not possible. That is, power can flow from AC to DC alone, and voltage is always positive. It cannot go negative. And it is called one quadrant converter, whereas this fully controlled rectifier is called two quadrant converter because voltage can be positive or negative. So this is a circuit we have taken for consideration, that is three-phase semi-converter with a freewheeling diode. So the information in the circuit diagram is made it in the tabular form. So T1, T3, T5. So T1, T3, T5 are upper devices. D4, D6 and D2 are lower devices. The numbering of devices has been already discussed in the previous three-phase full converter video. And thyristors, as far as thyristors are concerned, when it is forward biased, you have to give the gate pulse. So it starts conduction only after giving the firing pulse, and it gets turned off by natural commutation. Whereas diodes, so this will conduct. Now we have to find which diode will conduct at what time. So the diode which is connected to the most negative voltage will conduct first. Suppose A phase has having most negative value, then D4 will conduct. If B phase is having the most negative value, D6 will conduct. So the conduction period of the diodes remain fixed. Since 3 diodes are there, each diode will conduct for 120 degree. So now let us analyze the circuit for different firing angle. Alpha equal to 0, 15, 60 and 90 degrees. Let us consider the case for alpha equal to 0 degree. First, draw this line voltage waveform. If you don't know to draw this waveform, you can refer to the previous video where I have explained how to draw this waveform clearly. Then write down this conduction table which gives you the conduction period for each and every device. So let us take this period 0 to 120 degree. I am saying D6 is conducting. It means that D6 is connected to B phase. Here it is connected to B phase and it is a lower device. So when B phase is most negative, D6 will conduct. So if you see here 0 to 120 degree, you can see that this green and this brown, dotted line brown, are more negative. So what is this waveform green? VBC, and here VBA. Both are B phase waveform. That is the see the common term here. It is B phase. So D6 will conduct from 0 to 120 degree. Then 120 to 240, you can see here blue line and green line. So that is the most negative one. And what is the common term for both? C. So C phase device should conduct. What is C phase device? D2. So D2 will conduct. Similarly, you can write for D4. So now we have this period, conduction period of the diode remains same for the all the firing angles. Okay, that will not change. Now we have to see the conduction period for this thyristors. We have taken alpha equal to 0. So your starting point for a three-phase circuit, if you have a line voltage waveform, 60 degree should be taken as reference. This I have explained in the previous video itself. So 60 degree should be taken as reference for three-phase circuit when you draw the line voltage waveform. So that is fixed. So 60 degree is your reference. So, okay. So T1 will conduct from here. Then T3, when it will conduct, add 120 degree to it, so it will be 180 degree. Then when T5 will conduct, add 120 to this, so you will get T5 time period. So if you know to plot this one, you can make this table and you will get the conduction table like this. Okay. So if you are clear in this, it is easy to draw the waveform. Now let us fill up this table. That is, when T1 and D6 conducts, you have to write what is this, what will be the output voltage. So this also already explained. So I am directly writing. So what you have to do? T1. So T1, this one is in A phase and 6 is in B phase. So your output voltage will be AB. Why I am writing AB? Always write the upper device phase first, then lower device. So VAB. T1, D2 means this is A phase and this is C phase. So output should be AC. Okay. So here D2 is connected in C phase and this is B phase. So upper device first, so output should be BC. So similarly, you can fill up this one or you can refer to the previous video for detailed explanation. So after filling up of this table, now let us draw the waveform. So first time period is what is it? T5 D6. So T5 D6 means your output should be VCB, or you have to follow that VCB waveform. Where is VCB waveform? This one. So you follow this waveform till this point. Okay. Then what is the interval you have? D6 T1. D6 T1. So output should be VAB. So follow VAB. Then What is this? T1 D2 VAC should be output. So follow this one. So you can simply draw the output waveform. So this is your output waveform. So simply draw this one here. Mark this VCB, VAB, VAC. So this will be your output waveform. So you should be thorough with this one. It is not a complex table. You draw this, write this sequence, write the voltage correctly. And this only this table is important, that is the conduction period table. If you know this, drawing waveform is very easy. Next we will consider another case, alpha equal to 15 degree. So draw the conduction table. So D6, D2, D4 time period will not change. This same table from the previous case, that is alpha equal to 0 case, same thing. And this one alone for T1 60 plus alpha. So alpha is 15 degree. So I have made it as 75 degree. So you add 15 degree to this, you will get 195 degree. So T1, T3 and T5. So T1 it should start at 75 degree. Okay. So D6, D2, D4 already it is fixed. T1 you mark it. So T1 will be on till T3 gets turned on. So fill up the table. So table is ready. Now we can draw the waveform. This table remains the same for all cases. Now let us draw the waveform. T5 and D6. So T5, D6 output should be VCB. So follow VCB. Okay. Now next you have D6 T1 but for a very short period. D6 T1. What is D6 T1? VAB. So VAB you have to follow till this point. Okay. After that what you have? T1 and D2. T1 and D2. So output is VAC. So VAC till which point you should have? This point. So this one, then you have to keep it till this one. Okay. Now you can see that the waveform is not symmetrical. So if you draw this, you will get this type of waveform. So that is why I always say draw the line voltage waveform and you trace the output waveform from that, so that you can easily draw the output voltage waveform. Okay. So this is how your output voltage waveform will be. You can find that this waveform is not symmetrical. It follows some pattern. Okay. Now let us find the average value for this one. So how to find the average value? So what I am doing is I am taking as 60 plus alpha to 120 degree. Your output voltage is VAB. Okay. And 120 to 180 plus alpha, your output is VAC. So these two are different waveforms. That is, they have a phase shift in between them. So your integration is a very lengthy process in this case. I have given all the formulas how to solve this one. You can easily solve it. Okay. So VAB, if you are taking VAB as reference, and VAC will be lagging VAB by 60 degree. That you can see from the your line diagram itself. You see the VAB waveform and VAC waveform. There will be a phase angle difference of 60 degree. So sin omega t minus 60 degree. So since this term is coming, it may be a lengthy process to solve this equation, but it is very easy only. So I have given all the necessary formulas here. So if you solve this one, you will get this as the output. And still, if anyone needs clarification or all these steps, you can just mail me to read electric vehicle at gmail.com. I can send you the details. Next case is alpha equal to 60 degree. So again fill up this conduction table. So for diode, the conduction period remains the same. You find the conduction angle for T1, T3 and T5. So 60 plus alpha, 60 plus 60 will give you 120 degree. So let us mark T1 time period at 120 degree, T3 it's 240 and T5. Okay, so mark T1, T3 and T5. Now you can see from the conduction period that there are only three conduction periods: T5 D6, T1 D2 and T3 D4. In the previous case we had 6, but here only 3 periods are coming. So what will happen to the output? So first what you are getting, T5 and D6. T5 D6 is there, then T1 D2 is there. Okay, T1 D2, T5 D6 is there, T3 D4. T3 D4 is there. So this is not there, this is not there, this is not there. So your conduction table has reduced. Now let us draw the waveform. First one, T5 D6. What is T5 D6? Out should be VCB. So till 120 degree you should follow VCB waveform. Okay, then T1 and D2 VAC waveform. Follow VAC waveform till 240 degree. Then follow VBA waveform till 360. So this is your output voltage. Okay. Now we can see that there are only 3 pulses. Instead of 6 pulses as in a previous case, we have only 3 pulses here. So this is the peculiar phenomena of this semiconverter. Depending upon firing angle, its output waveform will change. You have only 3 pulses in this case. Now let us consider this case. Alpha equal to 90 degree. So for a diode, the conduction period remains the same. For thyristor alone, you find the firing angle. So we have taken alpha equal to 90 degree. So 60 plus 90 will give you 150 degree. So the starting point for T1 is 150 degree. Similarly for T3 is 270 and T5 it is 30 degree. Okay. You mark this one. You can see here there is some gap here. So it means that the T1 is not conducting for 120 degree. Instead, it is less than that. Why it is so? Because it starts conduction at 150 degree only here, and if you see this blue waveform, it reverses as at 240. So because of that, T1 gets turned off automatically. That is due to the reversal of supply voltage. Since supply voltage is getting reversed here, thyristor gets turned off automatically. But T3 is turned on only at 270 degree. So here only it gets turned on. So in between time, always a current will flow in the circuit only when two devices are conducting, one from upper device and one from lower device. Now T1 has turned off. So what happens? This cannot carry the load current. So in that case, freewheeling diode comes into action. So the current, since T1 has turned off, the load current start to flow through the diode, freewheeling diode. Okay, so thyristor, due to high firing angle, thyristor conduction period is getting reduced, and because of that, freewheeling diode comes into action. You can note that only for alpha greater than 60 degree only this freewheeling diode is used. Remaining time it is of no use. Now let us draw the waveform. So here also you have only three conduction periods. So I have written only those three. Now we will draw the waveform. So what is that? T1 D2 means output should be VAC. So VAC, follow VAC till this one. Then during freewheeling period output is 0. Then T3 D4 VBA is this waveform, brown color waveform, follow that. Then freewheeling period output is 0, and T5 D6 conducts VCB should be output. VCB is green color waveform, so follow that. So this is your output waveform. So hope you have understood. If you need any clarification, do mail to me. I can send you the details. So the points to remember here are, in three-phase semiconverter, output voltage is always positive. Freewheeling diode comes into role only for alpha greater than 60 degree, and this acts as a 6-pulse converter for alpha less than 60 degree and acts as a 3-pulse converter for alpha greater than 60 degree. Because we have seen that for alpha equal to 0 and 15 degree you get 6 pulses, but for alpha equal to 60 degree and 90 degree you get only 3 pulses in the outputs. These are some of the references, and if you like the video, do subscribe to our Read Electric Vehicle channel. Thank you.